Hello, is anybody there?
Hi, I'm Betty, Ke Chen. Oh, yeah.
Hello, just trying to see who's here. Hi, you've got your microphone on mute.
Yeah. Okay. Can you hear me now?
Okay. Hi.
Okay, that's better.
Yeah.
How you doing?
Professor Miller?
Hi, nice to meet you. I'm just double checking to see if anybody else is coming. I know some people, things happened, they're not able to make it.
Yeah, nice to meet you too.
Let's do 1, 2. I have 6 people who might be coming. I know at least 1 is not able to. We've got 3 people here so far.
Yeah, so we have 2 missing, maybe.
Okay, so let me just double check. I will send, I'll check emails. Okay. All right, I don't see anybody else having emailed me. And so, you know, given how late it is and how busy everybody is, I think we should start right now. So let me just say a few quick, oh wait, one email came in. Oh, 2 seconds. All right. That email was from somebody else. Okay. So let me just say a few words about myself again, and then we will start. So this is a bad echo. Okay. Typically, what you should do is you should turn off the video unless you need to share your screen, just because there are often bandwidth issues when people are in different countries. And I will be toggling and sharing my screen in just a moment. Okay. So the problem is I use so many different programs, it's sometimes hard to remember which is the command on each one. There should be it normally has a share screen option, which is not showing up right now. Interesting. Okay, can you see the slides?
Yeah.
Okay,
Yes, I
excellent.
can.
Is everybody able to see the slides?
Yes.
Okay, so
Yes.
you've gotten a welcome email from me describing who I am. Did you guys get a welcome email from me? Or if not, I can say a few quick words about myself. So
Yeah, I even like went to, sorry.
Okay, no. If you got the email, there's no need to repeat it, but if you haven't, I'll say a few words.
Okay. Yeah, I've seen it yesterday.
Okay. Is everybody able to hear me?
Yes, I can hear you clearly. It's fine.
Okay, excellent. Okay, so what I want to do is talk to you a little bit about some basics in cryptography. And what we're going to do tonight is not going to be directly related to the research project that we're going to try to get to. But it's important to get a sense of where things are, to see how things were done, and then that will lead naturally to the modern theory. So cryptography goes back thousands of years. If you could all just give me a little bit of a sense of what math you've taken in high school, what you've seen, especially related to number theory and calculus, that'd be very helpful, and that will help me pitch the lectures. So why don't we go with Kevin first, then Gordon, and then Jabo. So if you can just say a few words about your background. You know, what have you taken in math in high school? What have you seen in terms of number theory, probability, calculus? None of it is absolutely fine. I just want to get a sense of what people have seen.
Okay, I can start first if no one is
Okay.
going. All right, I took AP Cal BC in my sophomore year. I'm a junior, and I've taken multi-variable calculus, and I'm taking linear algebra in Johns Hopkins next year, and
Okay.
I've taken AP stats.
Okay. Have you taken any number theory?
I haven't taken any number theory, but I went to a math camp called Awesome Math in my freshman summer, and I studied like number theory for like 2 months.
Okay. All right. Who's next?
Okay, I think probably I'm next. Yeah, I've also taken AP Calc last year and multi this year, and I'm gonna probably take linear algebra next year.
Okay. So another very strong
Yeah.
background. And it looks like we lost Kevin. Are you still there, Kevin? Because we had 3 people a moment ago. We're down to just 2.
I think her name is not Calvin, it's Kaxin.
Oh, okay. Oh, thank you. We are down to 2 people, though. So this is... give me 1 second. Okay. So I just sent a quick email, and then I will have another window open in another device so that if anybody gets disconnected, I can hopefully see this. So the important thing to remember is that this technology allows us to communicate across the world. It sadly is not always perfect, but it is amazing what it allows us to do. Okay, so what I want to do now is talk a little bit about just some general thoughts. I've supervised over 300 students in research over the years, and just want to give a little bit of some like general advice. So the first thing is what questions to ask. There are so many different things you can research and study. You have to figure out, what do you find interesting? What do you think other people will find interesting? Who do you want to research these with? What techniques and methods do you want to use? The next is to try to explore and find the right perspective. So I just got an email in from somebody from the group. All right, so she's trying to fix it right now. There's an issue with the internet. This is why I've said to disable the video so that you're putting as little demands on the system as possible. Okay. So in a lot of problems, the hardest part is finding the right way to look at it. If you find the right way to look at these problems, they often become trivial. But finding the right way can be very challenging. And we're going to see a lot of examples of that in cryptography. The next point is to utilize what you know. So what are your tools? What are you good at? What have you seen? Is there a way you can convert whatever you're given to an area where you're an expert? And then the last piece of advice I like to give is control what you can. So there are some things that are going to be beyond your control, but you can control other things. For instance, when you are doing work, write up what you're doing as you go along. Don't leave it all to the end. When possible, try to give reports to me quickly. Try to get results that would be of interest to other people, and then write it up and submit it for publication. Go to conferences and give talks on it. So a lot of this advice is joint with students for many years. Another email coming in, let me just see. Right. Okay. So the first question, what questions to look at, how and with whom. So a lot of it is, building on what you know and what you can learn. So cryptography is a very challenging thing to study. The reason it's so challenging is people have been looking at these questions for thousands of years. So if you're going to try to find something new, you're going to be going against some of the best people in the history of mankind. Now, the good news is that anything you find that's new is almost surely going to be interesting. It might be hard to find a problem that's tractable with the tools that you have. So I am going to try to come up with a question for us to look at later in the summer that is related to things that have already been done, but maybe there will be a better way to do it. Or maybe there'll be some nice tweak or twist we can take on it. Even if we don't find anything new, we'll see good mathematics, we'll learn how to read technical papers, we'll learn how to write things up, and we'll at least be working in areas that other people find interesting. So that later, once you've taken more math and go further to the boundary, you might be able to find something truly new. But again, cryptography is an absolutely wonderful subject, but because it's so important, it's been extremely well mined. It's very hard to find new stuff in it. Okay, so very hard to ask interesting questions in general. We have a little bit of an advantage in cryptography, as I said, is in that we don't really have to convince people that this is interesting, that this is important. Looking for connections, this is hard. The more you know, the more different areas of mathematics you've seen, the easier it's going to be for you to see connections. This reminds me of something else. I don't know if any of you do math competitions.
No, I'm not very good at
Do
it.
any of you do math?
Oh, I do.
Okay.
I've
Excellent.
done some,
Do
but
you do,
not really.
okay. Do any of you do the geometry rounds?
Oh, yeah. In Duke Mass Meet, the AMT, American Math Tournament, and there's a geometry part.
Yep. When I was in high school, I always took the geometry round for my team. Most of my teammates hated geometry, and it had been so long since they had seen it. But for me, I wanted to take the geometry so that I would keep it fresh. And a lot of this is, what have you seen? Can you relate this to something you know? So more explicitly, this is my favorite piece of advice. And there's lots of different ways to phrase it. I like the last, it's short and sweet. If all you have is a hammer, pretty soon everything looks like a nail. And there's many ways to look at this. One way to look at this is, if you are really good with a hammer, then whatever problem you're given, you will convert to being a problem that is useful for the hammer. So have you all taken calculus?
Yes.
Okay, so if I give you a calculus textbook and section 3.2 is on the chain rule, and I give you a problem from section 3.2, what do you think is going to be useful?
Chain rule.
Yeah, chain rule, right? It's kind of hard to disguise, and in standard textbooks, they don't even try to. Life is not like that. When you're doing a research problem, it's not always clear what is the right tool or technique to use. If you have a textbook, the homework problems typically relate to the material that was just covered. So you have an advantage. Oh, I think I know what technique should be used to attack this problem. So if you're really good at something, you will try to view any problem you have in the lens of what you're good at. If you've ever heard of Richard Feynman, he was a phenomenal physicist, Nobel laureate. He was also very good at mathematics. He was a Putnam Fellow. And he had a reputation for being able to solve integrals that other people couldn't do, and he could solve them quickly. And in one of his books, he talks about how he was able to do this. And he said, look, I'm at Princeton. The people at Princeton aren't idiots. If they're giving me an integral, they've already tried all the standard tools and techniques. If it could have been solved with one of those, they would have solved it. They're smart people. They're not going to miss that. But a lot of people don't know the following integration technique, differentiating under the integral sign. So out of curiosity, have any of you heard of differentiating under the integral sign?
A little.
So it's a wonderful technique. It's a little bit harder to use. What you have to do is you have to convert the integral that they give you to a specific case of a more general integral with a free parameter, where you integrate with respect to that free parameter and then differentiate. And what Feynman said is, look, most people don't know how to differentiate under the integral sign. They don't know this technique. Let me try that first. And he would be able to solve a huge number of difficult integrals because the standard stuff he didn't even waste time with that. And people were just so impressed. This is one way to look at the law of the hammer. A better way to look at it is if you are really good with the hammer, go to the land of the screwdriver. If the people there could have solved the problem using a screwdriver, they would have. They're smart people. Because they haven't been able to solve it, it means something else is needed. So when I was in graduate school, I started dating somebody who became my wife. She was a graduate student at the Wharton Business School at the University of Pennsylvania. And her professors eventually found out that she was dating a mathematician. And they were like, can we talk to him? And I started working on a couple of very applied papers in marketing. And I introduced number theory and combinatorics in some very strange settings. And the reason is a lot of these people were very intelligent. If they could have solved the techniques using the standard methods in marketing or statistics, they would have. But because I had a different perspective, because I had a fresh perspective, I was able to do some things that they couldn't. And that's one of the things I want you to get out of this, is to be aware of what you're good at and then try to find places working with the same people with the same skill sets. It's going to be hard to do something new. When you do research, it's often good to have people not with identical skills, but with complementary skills. If you're really good at abstract algebra, you have somebody who's really good at analysis joining forces. Okay, so as I said, whenever possible, you want to try to write things up. The goal is to try to get a publication. Cryptography is a hard area to get a publication in, but we will try to do that. We'll see what we can do. Whenever possible, you want to get a reputation for being a good, fast, trustworthy person. So I always tell my students, no matter how busy you are, respond to any email in at most 24 hours. Even if it's just to write back and say, I'm really busy right now, I will get your email later. At least this acknowledges that you received it and lets people know that it's in your radar screen. As you get older, you want to try to find ways to do service to the math community, refereeing papers, writing reviews of articles for Math Scinet. You want to do things that help people get to know who you are. All right. So some prerequisites. So everybody here has taken calculus?
Yes.
Okay, so I don't know how much of this we're going to need, but just to make sure we're all on the page. Have you been told that one of the reasons we care so much about integration is because it can be used for probability?
No.
It's like area under the curve.
It's area under the curve, but have you been told why we care about area under the curves?
That's the density curve. Like area under the density curve is 1.
Yes. And did your teachers tell you that?
No, that's in AP Stats class.
That's
I
AP.
didn't have that.
But did your calculus teachers tell you that?
No, we just learned about the basic stuff.
Right. And so to me, I think this is almost a crime. To spend all of this time finding areas under curves without saying why we care about this. Calculus is the study of how things change. And you can go 2 different ways. You can take the derivatives and you can take the integrals. These are opposite operations. One of the most important applications, as was mentioned, coming from AP Stats, is that we can use this to find areas under curves. So I plotted a function over here. Okay, good. And if I have a probability distribution, it has to have a couple of properties. The first is it's non-negative, so P of x is greater than or equal to 0. The second is the area under the curve is 1. And then the third is the probability that my value of x is between a and b is just the area under the curve from a to b. You could also look at discrete distributions. You could look at mixed distributions. So the fact that the area under the curve is 1 just means something happens. And when you're calculating probabilities, probabilities shouldn't be negative. No matter how bad your team is, you shouldn't have a negative chance of winning a game. So then some of the more common things we talk about is we talk about the mean or the average of a distribution, which is just the integral of x times p of x. The variance is how spread out things are. It's x minus the mean squared. And if x is in meters, you would notice that variance is in meters squared. So if I wanted to talk about how tall people are, you could say on average people are 5 feet 6 inches plus or minus, and it should be plus or minus something in inches, not inches squared. Inches squared is an area. So we typically look at the standard deviation, which is the square root of the variance. And the last, and this is the plot that's up above, is the Gaussian, or the bell curve, or the normal. Anytime you have this many names, it's important. And so the Gaussian is very present in a lot of different settings. A lot of distributions, when you average, have in the limit this kind of behavior. And so the density is essentially exponential. And mu is going to be the mean, and sigma squared is going to be the variance. All right. So the next is just some basic combinatorics. Has everybody here seen factorials and binomial coefficients?
Yeah.
Yes.
Yes.
Okay, so I will do this just really fast. So n factorial is the number of ways to choose n people when order matters. If I only wanted to choose 3 people with order matters, it would be n times n minus 1 times n minus 2. And nck, or n choose k, is the number of ways to choose k people from n when order doesn't matter. So one way to find this out is to look at how many ways are there to choose k people from n when order matters, and then divide by the number of ways you could order k people. And then the last is Stirling's formula. Out of curiosity, have any of you seen Stirling's formula?
That's just approximation of factorial.
Yes. So you might have seen something very close to this in calculus when you did the integral test to try to find ways to approximate sums with integrals. So n factorial is about n to the n e to the minus n squared of 2 pi n. Okay. So now we're going to start, the real proper unit. We're going to move to Caesar and affine ciphers. So the first cipher we're going to talk about goes back to Julius Caesar. It goes back to Roman times. Back then, very few people could read. So just writing something down was almost enough to encrypt. One method used for encryption was to take a slave, shave their head, write a message on their head, wait for the hair to grow back, and then send them out.
Okay.
What is wrong, or what many things are wrong with this method of encryption?
I mean, like people can just shave their head again.
Yeah, so one thing is if the slave is get the message. If you know the message is hidden underneath their hair, shave them. So one of the big issues in cryptography is to make sure that only the intended recipient can read the message. So this is a huge issue with using slaves. What's another issue?
You can get into, wait, sorry.
There's not a key to it?
What do you mean by there's not a key? I mean, that's related to anybody can decipher the message. So that's the same issue. But there's another big problem with, taking a slave, shaving the head, writing the message, letting the hair grow back, and then sending them out.
I don't know. It is morally wrong.
I was wondering if anybody was going to bring that up. So I will ignore moral issues. I have a friend who's a philosophy professor who's teaching a summer class. I will leave those issues to him. Who here likes their hairstyle?
I don't hate it.
Does anybody like their hair? You don't hate it, okay. If I had you shave your head, would you be upset? If you became bald, would you be upset?
No.
A little bit.
A little bit. Would you be upset for the rest of your life?
Oh,
No.
so like.
Are you saying that slaves will be more likely to disclose?
No. How long would
So,
you
like-
be upset if I shaved your head?
Oh, before it grows back?
Okay, and how long will that be? Is it going to be a day? Is it going to be a week? A couple of weeks? A couple of months? A couple of years?
Oh, so like it takes a long time to encrypt?
It takes a long time to encrypt. If you want to send a message, you've got to shave the slave, write the message, and let the hair go back. Can you just send a message at a moment's notice? So one of the big things that we have to talk about in cryptography is efficiency. If it takes me 3 months to encrypt a message, that's almost useless. Now, I actually can think of a workaround for the fact that it takes here so long to grow. What I would do is I would take a bunch of slaves, especially their kids, I would shave their heads, and then I would write a bunch of messages on them. And then I would let the hair grow back, and then I would have a huge supply of ready-to-send messages. What might be a problem with this method?
So like you just increase the number of slaves that you're using by using their kids?
Yeah, so I increase the number of slaves I'm using. I set them off when they're little kids. I write messages on their heads after I shave them. Or better yet, when they're babies and they don't have that much hair. If the baby has hair, I shave it, write the message, let the hair grow, and then when they're older, I use them as a... What's the problem?
Not that updated.
I'm sorry?
The message is not updated. Like it was shaved when they were small, but when they grow up, maybe you don't want to send that message again.
You're very close. But that's why I have a bunch of slaves. So I have my choice of which slave to send. And I'll just keep track of which slave is which message.
Okay.
So I don't have to send a certain slave. I can choose which slave.
Are you saying it's like the single alphabetical encryption? Like mono-alphabetical?
What do you mean?
Like one slave means one message.
Each slave is a different message, correct. Maybe one message is declare war on Sparta. Maybe another message is seek peace with Xerxes.
But you will have limited amount of message depending on how many slaves you have.
Correct. Not only do I have a limited amount of messages, though, there's something even worse.
Or is it because like you have a lot of slaves so that you have to like provide like dwellings or food for them?
That's minor. That's not related to cryptography issues. But you're missing the key thing. When do I choose which message is on the slave? I have to choose the message when they're very young. You know, I have to give enough time for the hair to grow back. This method does not allow me to choose a message at the moment of time when I'm sending it. I can only use predetermined messages. That's a huge drawback of this. When we have people communicating, we want to be able to send any message at any time. So a method like this, by shaving the slaves when they're very young and writing the messages, I can have a whole stock of messages ready to go, but it's going to be only a finite subset and it has to be predetermined. So this is not a good system. We're going to concentrate on alphabet ciphers today, things that take the letters of the alphabet and apply rules to convert them to new messages. Later, we'll switch to more number theoretic systems. And the advantage of that is we can start applying mathematics. So in probability, when we talk about a random variable, you know, I could roll a fair die, and my random variable could be the outcome. And it could be, you know, a 1, 2, 3, 4, 5, or 6, and they would be equally likely. Or I could roll 2 die, and then what are the possible values for the sum of 2 fair die?
12.
What are the possible values for the sum of 2 fair die?
2 to 12.
2 to 12. Are each of those equally likely?
No.
Not
yes,
equal likely.
12.
No, in fact, you get 7, 1/6 of the time, because you can roll anything on the first die, and then the second die will have a 1 in 6 chance of giving you a 7.
Yeah.
And then you go all the way down to 2 and 12, which only happen 1/36 of the time. So in that case, not all the probabilities are the same. Now, if I toss a fair coin, that's another random variable. What are the possible outcomes of a toss of a random coin?
Heads or tails.
Heads or tails. The problem is if I use it as heads or tails, if I toss 5 coins and I get 3 heads and 2 tails, well, how do I combine a head and a tail? So a lot of times people will say, let's make a head be 1 and a tail is either 0 or -1. And then we can combine these. When we do random variables are always going to be numbers because we can then combine them. And when we switch to RSA and stuff like that, one of the advantages is because we're working with numbers, we can apply mathematical operations to them. So let's talk about an encryption function. So we're going to start with the alphabet. So we'll use the English alphabet for now, A through Z, although sometimes to illustrate a point, we might just work with a smaller alphabet. So I want 2 things to be true. I want different letters to go to different letters, and I want every letter to be hit. So I need both of these conditions. So one of the things we do often in mathematics is we try to say, what is the minimum set of requirements? Sometimes we are a little cavalier, a little loose, and we assume more than we need. And in fact, some conditions aren't necessary. Do we need both of these conditions? Or if the first condition is true, is the second true? Or if the second is true, is the first true?
If
Oh,
the
I
first
think
is true, then the second is true.
Okay, so does everyone agree if the first is true, then the second is true? Is this always the case? You have a function from a set to a set, different things go to different things, and everything is that always true? Or is there something special that makes it true in this case?
I think it probably like B can hit C and D can also hit C. It probably like A to Z except for C can all be mapped to C, and like C can be probably mapped to A or something.
Oh, yeah.
Well, it says different letters go to different letters. You can't have two things going to the same thing. So let's show the first condition implies the second. So different letters go to different letters. Is it possible that we miss a letter?
Yes.
So give me an example of how you can have different letters go to different letters and have a letter that's missed.
Well, then probably not.
I don't think so.
Okay, but can you prove it?
Like,
So we have the option of having some undergraduate TAs for a class like this. And so I'm going to occasionally say, this would be a really good problem to write up rigorously. So you should rigorously prove that different letters go to, that if different letters go to different letters, then every letter must be hit. So I'm going to give you an example where this is not always true. Have you ever heard of the Hilbert Hotel?
no.
No.
It's a mathematical hotel. It has infinitely many rooms. Every room is always occupied, and you always have room for new guests. Okay? So the rooms are numbered 1, 2, 3, 4, 5, 6, 7, et cetera, et cetera, et cetera. Imagine somebody shows up and they're a very important person and you want to give them a spot. But every room is occupied. How could you move people around between the rooms to free up space for this new person? So a new person shows up, they want a room, but every room is filled. What room should we give this person?
Oh.
You said there are like infinite amount of rooms,
Yep.
and not all of them are filled.
Every one is filled. 1, 2, 3, 4, 5, 6, 7. Infinitely many rooms, every room is filled.
Like, what do you mean by infinite?
So for every natural number n, there's a room number n. And every room already has a person in it. So when they show up, we have to give them a room. What room should we give them?
You said natural number, so it includes 0, right?
You can include 0 if you want. We can have rooms 0, 1, 2, 3. It doesn't really matter.
Okay.
Some people include 0, some people don't.
So if there's n woman and then the n plus 1 is also in infinite, but there's no woman in it.
Okay, say it again slowly.
Okay, so let's suppose that there's n-woman and it is infinite, but because it is infinite, so n+1 also exists, and that there's no woman in that place, so it's okay.
Well, no, but there's somebody in every room. So somebody's in room n+1.
But if we just define there's only n woman, but which n is infinite, then, okay, I don't know.
No, you can't do this. Every room has a person. You can't just define a new room that has nobody in it.
Okay.
But give me a room to put the person in. Every room is occupied, so you got to give me some room. What room should I put them in? You got to give me a room number. So give me a room number. There's a natural choice to do. What room should we put them in?
Natural choice? The
Yes.
first room?
The first room.
Same,
So let's say the rooms are 1, 2, 3, 4, okay? Put them in room 1. What happens now? There was somebody in room 1. We kicked them out of room 1. Where should we put them?
2. So we move everyone to the next spot.
Right, so this is very close to the suggestion of n+1. Just move everybody one room down. Were we able to squeeze in a new person?
But what about the last person?
If you just keep moving and then 4 to 1, then it's just a circle, but actually everyone is fake.
There's infinitely many rooms. There is no last person. If there were only 15 people, then we couldn't do this, because we could shift person 14 to room 15, but then there'd be no place to shift person 15.
Okay.
So what's the difference between this situation and the conditions for our function above?
One is infinite, but the other one is finite.
Yes. So those conditions might not be true. It might not be the case that the first implies the second if we have infinite setting. What if 3 people arrive to our hotel? Could we squeeze all 3 people in?
Yes.
How would we squeeze 3 people in? What would we do?
We'll put them in the first 3 rooms and move.
Yeah, just shift everybody down 3.
Yeah.
If 5 people or 20 people, we could handle that. What if infinitely many people showed up? Could we handle infinitely many people showing up?
Well, I think it will probably not.
So maybe we can handle finitely many people showing up, but not infinitely many people.
Because infinite amount of people will take infinite amount of rooms, but you only have infinite amount of rooms.
So if we just shift everybody over a fixed amount, that's not going to work. So as a homework problem, there is a way to handle infinitely many people showing up. You can't just be shifting everybody down a fixed amount. So I will let you think about that as well. When you have infinities, things can be very different. So part of the purpose of this summer is to give you some sense of how mathematicians think. What are the difficulties? What are the challenges? Anytime you have an infinity, you've got to be careful. But there is a way to handle infinitely many people arriving. Okay. Going back to our problem, though, it turns out that these 2 conditions are equivalent. If every letter is hit, then different letters go to different letters. If different letters go to different letters, every letter is hit. What's the simplest encryption function you can think of? We've got to map letters to letters.
Caesar.
Okay, so what is the Caesar function?
Like you move a letter to another letter. So like I think then the default setting is to move 3 spots. So it's like A is moved to D and B
Correct.
is moved to E.
Correct. So,
Function.
so basically, if X is our input letter, f of X will be the encrypted letter. And we can't use just f of X as a constant because then everything is being mapped to the same letter. So the next simplest function we can choose is you take your input X and you shift it down by C. Now we've got to be a little bit careful. What would W go to if we shift by 3?
I guess the remainder when divided by 26.
Right, but so W would go to Z, and then X would go to A. We would wrap things around. So it's basically using what's called clock arithmetic. If
It's like a circle.
It's like a circle, exactly. So if you look at a 12-hour clock, if it's 10 o'clock, what time will it be in 5 hours?
3.
It would be 3, because 15 and 3 are the same on a clock. As long as they differ by a multiple of 12, they're the same. So for an alphabet, we would be using things with a clock of 26 hours. And so we sometimes call this modular arithmetic, and we sometimes say mod 12. So, as was mentioned, C goes to E, so A goes to D, B goes to E, W goes to Z, and then X will go to A, Y to B, Z to C. So this is how to encrypt. How would you decrypt this message?
Move back 3.
Yeah, move back 3. It's not that hard to decrypt. And what's nice is the encryption and the decryption functions are very similar. They're both just shifts, they're just different choices. If one is shift by 3, the other would be shift by 23. So is this a good system?
No,
No. Why not?
because you can use in AP Stats class, like my teacher told me, like in a book, like if you draw out the frequency diagram of each alphabetical letter, it's going to be the same for each book, basically.
Okay, but that's overkill for this problem.
I think like if the slave was intercepted by somebody, they can also encrypt the message. Like during a war, if you're sending it to your like allies, and then probably your enemies can know what the message is.
So how hard is it for somebody to decrypt this message?
You can just guess for like 25 times or 26.
Yeah. Yeah, it comes down to, do you allow somebody to choose C to be 0? In which case you haven't really encrypted the message. So there's really only 25 or 26 choices for C. It's not that hard to decrypt. So there's a lot of advantages to the Caesar cipher. It's fast, it's easy to use, it's easy to decrypt, but it's not secure. So we want to try to make it a little bit more secure. Okay? So we could try a more complicated function. So the next most complicated function we could do is a linear function, ax plus b. So what values do you think would be possible for b?
Yes.
So let's look at a 6-letter alphabet, A through F. So we're looking at a 6-letter alphabet. What possibilities would there be for B?
Well, I guess all B's can work.
So tell me which values of B. So be explicit. Tell me what I could take for B. What are my choices?
I think all natural numbers B.
Okay, then that means I have infinitely many choices for B.
Yeah, I guess so.
I think B cannot be the
So
factor
can I-
of the numbers.
So B is just like a Caesar cipher. B is just a shift of everything, right? If we have a 6-letter alphabet, how many different shifts can I look at?
You can shift up most like 6 times, which is like back to its original
Yeah, so
alphabet.
Yeah, I can basically take B to be 0, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6, any 6 consecutive numbers. Right? If I shift by 1, is that the same as shifting by 7?
Yes.
Yeah. So there's really only 6 choices for B, and they're all fine. They all work. Because it's just shifting a message. So for analysis purposes, we might as well just assume B equals 0, because we can easily handle any choice of B. The more challenging part is what are the possibilities for A? So can you tell me what candidates we have for A? Maybe they don't all work, but what are the possibilities?
Just one and
1
5.
and 5.
Okay, 1, what else? I don't care if they work right now, just what are the possibilities?
Okay, then. And wait. I think 1, 2,
1 is
1,
6.
2, 3.
So you're taking too much time. What are the possibilities for A? I don't care if they work, just tell me what are the candidates.
1 to 5.
If I take A equals 1, it's just 1, 2, 3, 4, 5, or possibly 6. We'll see that 6 doesn't work, but there are 6 candidates. 1, 2, 3, 4, 5, 6, or 0 through 5. And then the question is, do all A work? So again, to figure this out, we might as well assume B equals 0 to make our life easy. And then if we want it to work, what must be true? If a value of A works, what must be true?
It's co-prime with the number of alphabet you have.
Okay, so that's the more advanced thing. You're coming up with which is really good. You're coming up with the answer. But what property should be true about the AX as we vary X?
Like we have to make sure that different letters, if the first condition must be satisfied.
Good. Different letters go to different letters. If 2 letters ever are encrypted to the same letter, we would have no way to decrypt. So now let's take A equals 1. And it works because if we look at AX, well, if the numbers are 1 through 6, then you get 1, 2, 3, 4, 5, 6 again. Let's take A equals 2. What do you get now when you look at 2x? What value do you get?
It's 2, 4, 2 to 12.
2, 4, 6, 2, 4, 6.
yes.
You get 2, 4, 6, 2, 4, 6. So this can't be good because 2, 4, and 6 each occur 3 times. And so if you get either 2, 4, 6, you can't decrypt it. And I claim right now that this is enough to know that 4 and 6 will also fail. Because if 2 fails, then if we apply 2 again to get 4, it's still going to fail. If we then apply 3 afterwards, it's going to fail. What about A equals 3? What would we get if A equals 3?
3, 6 repeated 3 times.
Yeah, it's even worse. What about 5? What do we get?
Right.
Five, five.
54316.
So does 5 work or does 5 not work?
It works.
Yeah, so if we apply it, 5, and then 5 times 2 is 10, and if you look at 10 mod 6, that's 4. 5 times 3 is 15, which is the same mod 6 as 3. But there's a faster way. When you get from each number to the next, we just add another 5. What's 4 plus 5? 9. And when we look at 9 mod 6, it's just 3. What's 3 plus 5? 8. And when we look at 8 mod 6, it's 2. Another way to look at it is 5 is the same as negative 1. So when we add 5, that's the same as subtracting 1. So it's going to be 5, 4, 3, 2, 1, and then we'll write 0, 6. And then 6 also tremendously fails. So 1 and 5 work, 2, 3, 4, 6 fail. And I believe somebody has already mentioned the pattern. So you want to say it again?
The workable A needs to be co-prime with the number
Yeah.
of alphabets.
A needs to be co-prime. So that's a great thing to prove, that when you're looking at AX plus B, if A is not co-prime, it fails. If A is co-prime, if A shares no factors with the number of letters, it will work. So that'd be another good homework problem. Okay, so what do you think is going to be true for a 26-letter alphabet? How many things will work?
Anything that's odd and is not 13.
Right, so we should have 12 things that work. So basically, it's all the odds but 13. So the Caesar cipher had 26 options. The Affine cipher has 12 times 26 is 312. So this is more than a factor of 10 better. Do you think the Affine cipher is secure?
312 is still not enough.
Right, not only is it a small number, but it's very easy to try the different codes. You know, there aren't that many things to try for the decryption. What if we tried a higher degree polynomial? What if we tried a quadratic? Do you think we could make a quadratic work? And that would give us even more choices.
Oh, by the way, I have a question.
Yes.
So, by secure, do you mean that there's a lower probability that somebody can decipher the message, or the expected number of steps, that expected number of trials that he needs is like greater if he wants to decipher?
I think those are the same, right?
They're pretty similar. We say message is secure if you do not expect somebody to be able to crack it without extra information in a reasonable amount of time. So for instance, if you know the A and the B in the affine cipher, it's very easy for you to decipher it. You subtract B, and then you multiply by A inverse mod 6 or mod 26, whatever the alphabet size is. So if you know the key, the choice of A and B, it's very easy for you to decipher. If you don't, you have to try all the different possibles A and B. So you have to try all the pairs negative B, A inverse. Well, there's only 312 such pairs. So you can try these pairs very quickly. And so we would say that the system is not secure because it can be cracked so quickly.
All right. Okay.
We're not.
Thank you.
What if we try a high degree polynomial? What if we try a quadratic? Do you think that would give us something even better?
But but like, how do you ensure that it's still satisfies condition 1?
Ah, so what might be the trouble?
What? Different x meaning the same fx.
Yeah. So it's not immediately clear that you can find a quadratic that will take different points, different inputs to different outputs, and that you'll hit everything. So as another exercise, can you find a quadratic that would work? And if so, then you might have even more choices. You'd have to see how many quadratics. So that's another problem you can look at. Is there a quadratic you could choose? And again, there are better encryption schemes than this. These problems are just meant for you to get a chance to see how well you're understanding the material, to just practice some math. And as I said, we do have the ability to have undergraduate TAs, so if you do want a college student to talk to, let me know. All right. So we're going to be using, in the discussions of RSA and other methods of encryption, the Euler-Toshin function phi of n. And it's been lurking in the background of a lot of our conversations so far tonight. So phi of n counts how many numbers from 1 to n are relatively prime to n. So if we go back a little bit, we saw for 26 that there were 13 odd numbers, but one of them, 13, failed. So there were 12 odd numbers relatively prime to 26. And if you look at this, what we said is what works for A is all possible numbers that are relatively prime to 26. Well, that's exactly what this function is. This function tells us how many numbers we have that are relatively prime. Now, just because we've given a function a name doesn't mean we can work with it. So the question is, can we compute phi for various choices? So the simplest thing to look at is phi of a prime. So how many numbers from 1 to p do you think are relatively prime to p? So we'll say two numbers are not relatively prime if they're both divisible by a number greater than 1. So 1 will be relatively prime to everything. So 4 and 12 are not relatively prime for both.
So it's just p
P
is
minus 1.
Yeah, it's just p minus 1. The only number from 1 to p that shares a factor with p is p. Well, n is always going to share a factor with 1. So this has as many numbers relatively prime as possible. And what about phi of p squared?
Guess
P
anything that's
squared.
co-prime.
Co-prime with p? Like p, the multiple of p. Like,
Well, it's
I
going
think
to be co-prime with p squared. But being co-prime with p squared is the same as being co-prime with
I think it's just phi of
Are you
p.
still there?
I think it's just phi of p plus. No, I think it's phi of p squared minus everything that is multiple of p.
When you
So
say
is that
phi of p, when you say phi of p squared, is that p minus 1 squared? I can't tell where you're putting your parentheses. So one of the things you should always do in problems like this is gather some data. You know, it's not that hard to look at things.
Oh, it should be p squared itself minus the number of multiple of p, I think.
Yes, so, and how many multiples of p are there up to p squared?
P?
P, right? We have p, 2p, 3p, 4p, all the way up to p times p. So there are p squared numbers, and then p of these numbers have a common factor with p. So p squared minus p will be how many are relatively prime. What about phi of p cubed?
I guess
P is
P.
square multiple P minus 1.
I'm sorry, I couldn't hear you. Could you say that again?
Well, I'm going to have class, so I can't speak anymore now.
Okay. All right. Have a good
Yes.
one.
Okay, thank you.
So I guess this one's p times v p squared.
Yeah. Or we can write it as p cubed minus p squared. We have p cubed numbers, and then p of them are going to be multiples of p. It turns out when we do RSA encryption, all we need is to handle the case when n is a product of distinct primes. So what do you think phi of pq would be?
So
Phi of
okay.
p. It should be phi of p times phi of q, if p and q are coprime.
Right. And in fact, this is true in general, and that's a great exercise. If n is a product of any two relatively prime numbers, a and b, then phi of ab is phi of a, phi of b. And this allows you to figure out phi in general just by knowing it at prime powers. But how could we prove what phi of pq is? Well, let's look at the multiples of p that we lose. We lose p, 2p, 3p, all the way up to qp. What about the multiples of q that we lose? We lose q, 2q, 3q, all the way up to p times q. And the only element that's in both of those is the last one. So we take pq, how many numbers we have, we subtract off the q multiples of p, we subtract off the p multiples of q, and then we add back because we subtracted off qp twice. And when you do a little bit of algebra, you see this is just p minus 1 times q minus 1. So this would be an important function later. As a nice exercise, try to prove if a and b are relatively prime, phi of ab is phi of a, phi of b. All right, so let's talk a little bit about some permutation ciphers. So one of the problems, and you mentioned this earlier, is if we always send the same letter to the same letter, this is vulnerable to a frequency analysis. So in the English language, the most common letter is an E. So if you look at one piece of text, if you just look at how many times each symbol occurs, whichever one is the most common is probably the E. So the Vigneri cipher was a way to try to fix this by sending the same letter to different letters. So what you do is you take a key phrase. I chose ABC, ABC, but you would want something more complicated and longer. And what you do is you write that message that you want to send on top, and then you keep writing your key phrase underneath. And then what you do is you just add in columns. So D, underneath it is A, so we shift D by 1, and we get E. The next one, A is underneath, A is over B, so we shift A by 2, and we get to C. Then D is over C, so we shift D by C, which is 3, so we go to G. So notice that the letter D, the first time it's sent to E, the second time it's sent to G, later on it's sent to F. A is shifted to B and C. So what's nice is the same letter is sent to different letters. So if you see, an E, an F, or a G, they could be a D. They could also be other letters. So D, if you look, C is shifted to D from the fourth letter, and then the third to last letter, B, is also shifted to a D. So when we got a D, it could have been a C, or it could have been a B. So how secure do you think this is? Do you think this is more secure? Could it be less secure than the Caesar cipher?
Probably.
So So do you think it could be less secure than the Caesar cipher?
As long as the key is very short.
But do you think it could ever be worse than the Caesar cipher? So what's
No,
the shortest
because
key we could have?
if the key is 1, it's basically the Caesar cipher.
It is the Caesar cipher. So this is a generalization of the Caesar cipher. It can't do worse. It might not do better, but it can't do worse. If you have a key of length 5, you now have 26 to the 5 possibilities. So this is a lot better. And the longer your key phrase is, the more secure it should be. So for a long time, people thought that this was an unbreakable cipher. And then it turns out it's very easy to break. Okay. So the first thing is, it's called like the Kruskal algorithm. People can actually figure out the length of the key phrase by doing some advanced mathematics. So imagine you know that the length of the key phrase is 8. What you do is you break your message up into 8 sub-messages. You look at every 8th letter. And then you apply frequency analysis on each one of them. So it turns out you can still use... Exactly. And this illustrates the dangers of cryptography, that things that seem secure turn out not to be. People thought this was extremely secure. A couple of years ago, they discovered a message from the American Civil War in code at the bottom of a river by the city of Vicksburg. And it was written, and it was encrypted using a method like this. And of course, it's trivial to break this with modern computers, but people had fun and they cracked it by hand. And what happened was the courier who showed up to Vicksburg to give the message to the Southern General Commanding saw a Union flag flying over the city. The Union had just taken it the night before. Well, since the Northern forces had taken the city, there was no reason to deliver the message. He just threw the message into the river. When you decrypt the message, it says, greetings. Unfortunately, we have no troops to spare. You are on your own. Good luck defending the city. But no problem cracking 100 years later. So one last thing that we'll talk about for the last one for today is permutation ciphers. So there are 26 letters we could send A to, 25 for B, and so on. And so how big is 26 factorial? Well, when you do the multiplication, it's about 4 times 10 to the 26. This is a lot better than 312. Do you think 4 times 10 to the 26 is too many things to just try by hand?
Yes.
Yeah. So if you do a little bit of a calculation, so I'll have you do this. Imagine you have a supercomputer at your disposal capable of doing 10 to the 9th codes a second. Calculate how many seconds there are in a year, and calculate how many years it would take for you to check 10 to the 9 a second. You could even go up and say you could calculate 10 to the 12 codes a second and see how many years it would take you. So if you're doing just a brute force analysis, this is very simple.
So you use the Stirling's approximation to do that?
No, I mean, I actually just multiplied it all out. I have computers that can do that. That's no problem. You could estimate that. That's not a bad idea, is to just see what would Stirling say for 26 factorial and see how close it is.
Okay.
Do you think this is secure?
With a supercomputer, no.
Well, I'm saying even if you could do 10 to the 15 per second, you could do the calculation. I think there's on the order of maybe 10 to the 9th seconds in a year. So how many seconds are there in an hour? In a minute? How many seconds in a minute? 60?
Yeah.
Let's make it a little bit easier because we're going to do this in our heads. Let's say there's 100 seconds in a minute. That's 10 squared. How many minutes in an hour?
60.
let's make it 100 so it's easy. That's 10 to the 4. How many hours in a day?
24, 20.
Well, let's run it up to 100. So now we're at 10 to the 6. How many days in a year?
Doing it.
So let's run 365 up to 1,000. That's 10 to the 9. So there's less than 10 to the 9 seconds in a year. If we had a supercomputer capable of doing 10 to the 12 checks a second, in 1 year, they'd get us to 10 to the 21. Imagine you have 100,000 supercomputers. That's 10 to the 5. So you had 10 to the...
So we need 4 years.
Well, we had 10 to the 12, 10 to the 9 is a year. That would be 10 to the 21. So if we had 100,000 supercomputers, it would take us 1 year to do. Do you think this is...
No.
You know, do you think most organizations have 100,000 supercomputers just available to do something like that?
I don't think so.
So if you just do a brute force attack, I think it's pretty secure relative to a brute force attack. But you've already mentioned how you could crack this. What could you use to crack this? So you've already mentioned this for other stuff from your AP Stats class.
Oh, the frequency? Wait, no.
Yeah, you can just use frequency analysis. Because every letter is always sent to the same letter. That's why the Vigneri cipher was better, because the same letter could be sent to different letters. So if you ever see, there's a lot of times when they have these daily cryptograms, they include spaces, which makes things a lot easier. In the English language, there are only 2 one-letter words. What are those words?
Okay. Professor Miller, I have a question.
Yes.
So, so for the last method, so if like instead of doing just one round of one round of ABC, like if we did like the first round ABC and then we further encrypt it with probably like BCDE, and the third round probably XYZ, would that be like more secure?
Well, that would just be doing a Vigneri cipher with a longer keyword. Right? You're just changing the length of your key phrase.
Yeah.
In general, the longer the more secure it is.
Okay, so
we'll
sorry.
So what often happens is the Vigneri cipher is very fast to use. RSA is significantly slower. So what you would often do is you would use RSA to send like a Vigneri key phrase, encrypt the message using that, and then you can transmit things much faster. So even though these things have issues, if the key phrase is sufficiently long, you're not going to be able to do a good frequency analysis. So, going back to this case, the frequency analysis is not so bad. There are only 2 words in the English language that are one letters. It's I and A. So if you have a long text with spaces, you can probably get those letters pretty quickly. The word the is often very easy to find. It turns out this is not that secure. So what I'll end today with is talking about why we use primes. So I want to just quickly describe 2 different systems and then we'll end here. So in the first, P and Q are 200-digit prime numbers. I multiply them together and I get a 400-digit number n. I make n public, so you know this product. And the password is either P or Q. So there are two different passwords. The other is I take a 5,000-digit random number X, and that's the password. So which do you think is harder to guess? The 5,000 random digit number when you're given no information, or either P or Q when you're given their product?
Product.
Wait, what do you mean by given the product? So like you're given N and you want to solve P or Q?
Yep, I tell you what N is, and you have to give me either P or Q to get in, and N is 400 digits. And you have to give me one of the 200-digit numbers that divide it. You think that's easier or harder than guessing the 5,000 digit?
I guess. Wait. Sorry, never mind.
I guess if you're talking about a power of random numbers, then the first will be harder. Will be more secure, I guess.
So you have to give me a 200-digit password. And you know that it has to divide N, and N is public. Or you have to get 5,000 digits correctly. So you're saying you think it's harder to get 200 digits when two different ones work than to get 5,000 digits? So I can forget that I know what the product is N. I can just say, look, it's a 200-digit passcode. I can try all 200-digit possibilities. Shouldn't that be faster than trying all 5,000-digit possibilities?
Yeah.
So which do you think is more secure, the first method or the second?
Wait, so like for the first one, you only give an N, but you need to figure out how to factor out N, right? And
Well, if you knew how to factor, you could just factor N. But even if you don't know how to factor, you can just guess. You're guessing a 200-digit password versus guessing a 5,000-digit password. Which do you think should be harder to guess?
well, I guess the second one's harder.
The second one. It turns out the first one is harder. And the reason is, does the computer need to know the password in the first case? How can the computer tell if you got the password correct?
Correct.
So all the computer needs to do, since it's getting late, it knows what N is. The computer doesn't need to know P and Q. How can the computer tell if your guess is correct?
Divide N by your answer if it has another prime and 200 digits.
No, you don't even have to see if it has another prime. Just divide N by your number, and what does the computer look for?
A 200-digit number?
No. If your number is a factor, what will happen when you divide N by your number?
Oh, the other answer? Wait.
Close. What would happen if you divided N by something that's not one of the factors? Let's say N is 35, and you divided N by 11. What would happen?
Oh, to see if the result is an integer or not.
Yeah, just see if the result is an integer. See if the remainder is 0. The computer doesn't need to know the answer. But if it's a 5,000 random digit number, the only way the computer can tell if you're right is the computer must have the password in memory. And you have the ability to torture the computer, to capture it, and to try to force it to share its secret.
Okay.
And even though there's a lot more 5,000 digit numbers than 200-digit numbers, and I just give you a calculation here just how bad it would be. And I'll let you read that later. There are so many primes that you just can't check this by brute force. And it goes to the point where if every atom in the universe was another universe, where every atom in that was a supercomputer doing now 10 to the 15 things a second, and you looked at the life of the universe, you wouldn't even be close. So if you had been running a universe of universes of supercomputers since the dawn of time, you wouldn't be able to check everything. So this is one of the reasons why we use primes. All right, so what I'm going to do now is I'm going to sign off, and I'm going to try to make the video available to everyone else. And then have a great evening all, and looking forward to talking to you guys again.
Okay, thank you very much.
Thank you
Take
so
care.
much.
Bye. Good night.
Have a good night.
All right, have a good night.